Problem statement from GATE Physics 2016 paper reads as follows. The number density of electrons in the conduction band of a semiconductor at a given temperature is 2 into 10 to the power 19 per meter cube. Upon lightly doping this semiconductor with donor impurities, the number density of conduction electrons at the same temperature becomes 4 into 10 to the 20 per meter cube. The ratio of majority to minority charge carrier concentration is. This is a numerical answer type question, and so we'll provide our answer in terms of numbers. Now, look carefully at the question. It says that number density of electrons in conduction band of a semiconductor, that is given to us, and then it says upon lightly doping this semiconductor. This means initially semiconductor is undoped. Semiconductor is undoped, or we can say it is intrinsic. And we know that for an intrinsic semiconductor, number of electrons in conduction band is equal to number of holes in valence band is equal to the intrinsic carrier concentration, which we denote by the symbol Ni. Now, the number density of electrons is given is 2 into 10 to the power 19. So, this implies we get Ni equal to N, and we know N has been given as 2 into 10 to the power 19 per meter cube. Now, what happens is that then this semiconductor is lightly doped. It's written here, is lightly doped. Now, there can be two type of doping, donor doping or acceptor doping, and it is given that it is doped with donor impurities. Now, what are donor impurities? Donor impurities they have an excess electron, so they donate the excess electron to the semiconductor. So then we dope with donor. This is the second case, and such an semiconductor is known as extrinsic semiconductor. In this specific case, since we have doped with donor, this will become an N-type semiconductor. An N-type semiconductor will have majority electrons and minority holes. Now, let's try to determine the concentration of electrons and holes. It has been given that the number of electrons after doping, so number of electrons after doping becomes 4 into 10 to the power 20 per meter cube. Now, what happens to the number of holes? Let's assume the number of holes after doping is P. We don't know this value, but we do know that law of mass action will still remain valid. That is Np equal to Ni square. Note that this doping, this left side as well as intrinsic as well as extrinsic, is happening at the same temperature because it's written in the question. So earlier when it's undoped, let's say it's at some temperature, let's say 300 Kelvin, room temperature, and after doping the semiconductor remains at the same temperature. Hence, we can apply the law of mass action. Np equal to Ni square. Now, what is the value of N for doped semiconductor? It is given 4 into 10 to the power 20. What is the value of holes in this N-type semiconductor? We don't know. We'll assume it's P. And Ni. Ni is the same as before because we have not changed the temperature. So, 2 into 10 to the power 19 squared. This will give me P as 4 into 10 to the 38 divided by 4 into 10 to the power 20, which is 10 to the power 18 per meter cube. Now, we were required to find the ratio of majority to minority charge carrier concentration, and we know that in N-type, majority are electrons. So, I can say required ratio is equal to, majority is electrons, so their concentration is N, holes, minority is holes, so minority is P, and the value of N is 4 into 10 to the power 20. The concentration of holes is 10 to the power 18. So this will come out to be 400. So this is in n-type. So the required ratio in n-type semiconductor, it comes out to be 400, and that is our answer here. So 400 is our answer. Thank you for listening.